talk a little bit about when it's not straight lines that things move along today. So mostly stuff we've been doing over the last couple of years. Slightly different direction maybe than focusing on the cosmic web in itself, where we try to mostly, can we sort of, what are the requirements for precision era cosmology from the simulation side? Can we bring together perturbation theory and simulations? And so this was done with a lot of people in collaboration, of course. So maybe just in case you didn't know this, so that's sort of what we're trying to simulate. And I will not go quite to the galaxies here, but just to highlight here, when we're doing simulation or when we're doing all this modeling, there's sort of, how to say, a break in what we're actually doing, because we're describing the early universe with an Einstein-Boltzmann as a very complex, coupled multi-physics system. And then we transition to not linear, but non-linear models, but we drop most of the physics because we assume sort of it becomes irrelevant.
Speak for yourself.
Huh? I speak for myself. No, I speak for the large-scale structure community and the large-scale structure cosmology, of course, here. And exactly. Well, you don't include relativistic effects, maybe. Okay, so in some sense there is some problems how to exactly match these things together, and so there were, I don't know if I could talk probably for an hour about this, and you get very, very bored. But there's one sort of rigorous way that we kind of think is the right one, that we actually go all the way to today with these Einstein-Boltzmann models, and then we go all the way back with a sort of a reduced linear model where we drop all the extra physics, and then we can go forward and we get all the non-linearities correctly. And then, okay, now this is frozen. No, here we go. And so we can describe then this sort of non-linear regime with perturbation theory. Lagrangian perturbation theory is particularly well suited. And so unfortunately, we have this kind of nastiness. So this is a space-time diagram of a single one plus one dimensional perturbation. And so we have the straight lines, which are Zeldovich, but then we have this nasty shell crossing. And so sort of everything that's inside of this caustic surface here is inaccessible, or has been inaccessible traditionally to perturbation theory, while everything that's outside sort of is still rigorous. And so you see very nicely in 1D that everything that's outside the shell-crossed region is still perfectly well described by the Zeldovich approximation, by being straight lines in the correct time coordinate. But everything that's inside sort of does something crazy. And so you have a very peculiar thing, that there's a moment in time when actually this sort of this simple approximation breaks down. But apart from everything that ends up in here, it's actually perfectly still valid. So how much do we actually know how this generalizes to more than 1D? So we know this is particularly simple in 1D because, well, otherwise you wouldn't get straight lines. In fact, you don't even have a perturbation theory in 1D because it's correct. There's a Zeldovich solution, which is the exact solution in 1D to shell crossing. So in multi-D, of course, this is very annoying with this spinning ball. I have no idea why that is. Okay, so in more than 1D, of course, everything becomes a bit more complicated. You get the map, a more general mapping, but we know how to do this for a while now. You can write down sort of a perturbation series for this, and this includes kind of the coupling of Zeldovich to itself, and so on and so on and so on. So it's a standard perturbation theory, and of course it goes to infinity, and we cannot calculate this. But we have recursion relations, which have been the first one to develop this was Cornelius Rumpf, who's been involved a lot in this work. And so we know actually how to calculate these now numerically. And so if you know Zeldovich, you can calculate the next one. Then you know 2LPT, you can go on, and so it can keep going on. So how does this actually, I jumped ahead. So one question is, does this actually converge? Where does it converge? And how long does it converge? So you might not care about this, but it's a valid question mathematically. So the problem is always, if you have, maybe you remember from the Mathematics 101, Analysis 101, if you have a complex plane, you expand the series around something, then there will be at some point, either it converges everywhere, if it's an analytic function, or if it's polynomial, or if you have a singularity, wherever in the complex plane, then you're done, right? This is where it ends. Okay, so the question is, even if this isn't happening on the real time axis, this could be the end of it. So what we wanted to understand is, is LPT actually convergent? So now we calculated all these terms. I don't think anyone has really done this before. So you see, this is 1 LPT, 2 LPT, 3 LPT. This is sort of the spatial coefficients of this whole thing. And so you can now check based on this, you can see actually does it converge. And so the interesting thing is almost everywhere can you go further than the first shell crossing, which is sort of already comforting. Especially you can go in some regions, like in Zeldovich, you can go further than the first shell crossing happens globally in the field. But what's very interesting is, well, there's a whole paper, if you're interested in this, I can recommend this. But you see there's actually a very interesting structure to these coefficients here. So 1 LPT, Zeldovich, has a very different structure from 2 LPT. And then they sort of stay more correlated. And you see you have this kind of set of points which survives forever. And so this, in fact, we dug a bit down. This has been known for a while, that Zeldovich approximation doesn't work very well in voids and for spherical collapse and clusters. So there is a set of points which are exactly, precisely, if you then look, the centers of voids and the centers of the clusters in this case, or the halos, where it doesn't converge very, very easily. So you can actually look at this. This is the spherical collapse solution, and you've all calculated this in your Cosmology 101 class, right? This is the parametric solution. Now you can actually throw LPT at it. You can derive the recursion relation, so you can actually do this up to 30th order with Mathematica very easily. And so you see, it bends down here very, very slowly. And well, this is the reason for this. And this is the reason for why, of course, many people have adopted sort of UV completions for this, where you just cut off sort of this regime and say, okay, I approximate this with some model. But we'd like to eventually do this better than these ad hoc models, but we're not quite there yet. So if you paid a little bit of attention to the picture with the radius, then, well, if there is a symmetry in the field, this should hold for the other region as well. And so if you go to negative A or negative curvature or negative overdensity, all the same thing, we should have the same radius of convergence. And in fact, this is the reason why in voids also LPT does not converge. So you have no shell crossing in voids, but your series, your LPT series, does no longer converge. Oh, because you're adding higher and higher momentum in some sense, right? And it does not converge anymore. Exactly. No, so I don't have time. We can do an extra talk if you want as part of the workshop. So there is a way, at least for the spherical collapse, we know how to fix it. You can derive a rigorous renormalization group calculation which fixes this. But for this we needed to use some things which for the general field we do not have. And so we know how to fix it in 1D, but not yet how for the field. Okay, so I wanted to quickly go. So this is all nice and good. So what do we learn for n-body simulations? So simulations now, instead of having this continuous mapping, we have like our simulation building blocks, which we push around and do our discrete thing. And so, of course, we have the problem that instead of being in the continuum limit, we are in the particle discreteness limit. And so one thing we realized, I think it's been known to some people, but maybe not really appreciated enough, is that because of the discrete nature, actually you have an anisotropic growth factor in your n-body simulations. So your D plus in your theory, linear theory, actually is anisotropic, and it's almost nowhere except in the very center exactly the linear theory growth factor that you want to have. And so what happens is, because of that, is that you have not the correct growth. You have the discrete growth, not the continuum growth in the simulations. And so because we have this sort of higher order way of doing things now, you could actually see that if you start your the earlier you start your simulation, the more are these kind of wrong growth imprinted in your simulation. And so it's much better to start much later with a higher order perturbation theory rather than earlier with a simulation. And so this goes a bit against the old philosophy that, well, you should do it the other way around. Something else we worried about is, well, it's kind of weird that you have to do so many time steps in a simulation in the first place to reproduce the Zeldovich trajectories, which are effectively straight lines, right? So if you look at, this is the one-dimensional problem. If I want to have a machine precision error, not that anyone cares about this, But then, and I use a standard second order integrator. You see, I have to do in excess of probably 1 million time steps to do this, which is ridiculous to reproduce a straight line, right? So why is that? Of course, there has been one solution to this in the literature, which we already heard about earlier today, which is the FastPM scheme. Unfortunately, in that paper, they proved no properties of such integrators. And so we actually, I don't know, we're not so happy. So we looked at this again, and we found actually there's a whole classes of integrators which have these properties, that they're exact in the perturbation theory sense. So the idea is that you know that for standard second order integrator in a simulation, it's a parabola. And you can just say, if I choose the same time coordinate as in the perturbation theory, I should be able to match the whole trajectory exactly to the perturbation theory. And you can do this, and then all these are basically machine precision correct up to second order perturbation theory. And so you can do now power spectra with very few steps. This is the original FastPM, and these are our new integrators. So they are, you get linear theory correct in an n-body simulation with 2 steps. And then you have a rigorous, it's not approximate in that sense, but it's a rigorous converging scheme. So you can prescribe an error, and you have to do so many steps to be under it. Something else in this line, okay, if we have 2 fluids instead of 1, then the problem was always we didn't get the relative growth correct. I don't know, this cost me a year of my life, like 7 years ago. We didn't really fix it. We thought back then you have to add a larger softening. There was also a paper by Simon Bird about this where they claim that you solved this problem with decorrelated particle arrangement. So again, discreteness effects sort of completely wash out the small difference between baryons and dark matter. And so looking at this with a bit of distance actually helped. What's actually causing the difference between in amplitude between dark matter and baryon perturbations is not that you should think of that the particles are differently displaced, but that it's really isocurvature perturbations. So the particles should start with sort of perturbed masses that are sort of reflective of these isocurvature perturbations. And when you do this, then you get this full thing correct. So you see here, if we had imprinted this relative differences between baryons and dark matter in the particle positions, we would get the gray line for the ratio of the baryon to the CDM power spectrum. And if you perturb the masses and then pull off your NLPT scheme on the displacements, you actually get the correct one. And so you also get this very nice nonlinear suppression in the baryon bias. Okay, last thing I wanted to talk about. How many more minutes? 5, okay, excellent. One last thing we were wondering about, so pushing particles around is nice and good, but with Tom also we worked a lot not to have to do this. So another way of not having to move particles around is actually something that I think Cora Uhlemann also talked about this earlier at the meeting, is that you can map Zeldovich to a field-based version where actually you recast it as a corresponding Schrödinger equation. And so you think of similarly to having sort of your relation between Lagrangian space from where somebody comes and Eulerian space where something goes as a transition probability, very similar to actually what Ravi Sheff was just telling us. And so, and the Zeldovich, then it's sort of, you get this probability is highest when the distance is minimized. And so, but you can fully recast this then sort of as a Schrödinger-like equation. And so something, what I thought was very cute is that the phenomenon of multi-streaming becomes simply quantum interference, right? So similarly to a particle, a photon going through the double slit, you have, it's coming from 2 Lagrangian positions basically and overlapping the same point. And so this is basically the same picture you've seen at the very beginning, the space-time diagram of a single mode perturbation, but of course this is Zeldovich, so there is no bending back of the trajectory. And so it looks like this. It was in fact Peter Kohls was the first one sort of to point this out, but only for Zeldovich. And you can actually upgrade this fully to higher order as well. So then, unfortunately, you end up having to solve some, or approximating, we can't solve them, approximating some path integrals, but you can, for example, we did it for the equivalent of the next orders just to prove. So you have Zeldovich, and then you get this out from the free propagator to LPT. You have one interaction term, so you see the inner structure is always exactly the same here. Now you can apply this to random initial conditions, so power spectrum, CDM, lambda CDM power spectrum. For example, we use this for ICs for Eulerian codes, which always had the problem that if you have a grid, you can't really, you would have to interpolate your particles back in order to get grid-based initial conditions, which are consistent with this. But with this way, we can actually do it. So you see, you get this very non-Gaussian velocity fields here because they're actually displaced in some sense. So this is built into this code that you, if you're interested, you can download and play around with it. And I'm just skipping over this so we can now compare, for example, in much more detail, much better output of things like Ramses, grid-based codes and particle-based codes on summary statistics. But just to make another connection with the field-based modeling, what we liked about this is that you, of course, now we have continuous fields. So this is the Zeldovich approximation. So we have now in this propagator perturbation theory, well, we could have sort of gridded the particles and then smoothed, but here we get sort of a field-based realization in one go. We don't have to go through particles, and we have, thank you. So we get the full thing at the field level. We can even propagate from Lagrangian space to Eulerian space to redshift space in one go, because at least in Zeldovich and these things, this is fairly straightforward to do. And you can add one more thing, one more step to get then the redshift space transmitted flux using fluctuating Gunn-Peterson approximation. And so I have a very, very quick forward model, which could be used for tomographic. And so we had with Natalia Porkeres, actually, we looked into applying this to Klamato. And so if anyone's interested, I really like this approach. So of course, it's only accurate on some scale. So if you want to do better, you probably have to fix it up with something. But then all of these models are only accurate so and so much on these scales. Good. So I want to just advertise one last thing, because there's some people working on Galaxies here as well. So something else that we've been working on is the Cosmic Web. Actually, it's CosmIC Web, which is a big database of proto-halo patches for large simulations. And so this was just something. So if you're interested in this, talk to me. You can already sign up here as well if you're interested. So for the Zoom simulations of very high-risk galaxies, everybody always goes through the same steps and so on. And so we thought we automatize this. And so we have a big database, and you can just say, okay, I want to observe numerically a galaxy with these and these properties, say at redshift 2, no mergers since redshift 3. You just click your thing. You get an ID and the IC file, and you put the ID in your paper, and everybody else can reproduce it. And so this is the Cosmic Web. So if interested, get in touch. This is all wonderful work done by my former PhD student, Michael Bühlmann. Good. I leave you with my, I have 1 minute left. No, it's just, you can read this yourself. Thank you very much.
Hi.
Thanks. I'm very curious about the Schrödinger equation to cast a kind of phase space diagram, and it's noticeable that even in the classic Zeldovich regime, there's still like ringing features in the velocity for the velocities. I wonder.
This one?
Yeah.
So what you should see, this is aliasing from the projector or from the imaging. So what you should see here is that lines of constant color are lines of constant phase of the wave function. So they correspond to classical trajectories. Okay. And so this little ringing that you see here is purely because of the pixelization and some kind of aliasing from the projector. So here it's perfectly smooth. It's only then when you get to the regime where the shell crossing happened that you start getting these nodes. Yeah.
All right. Okay. Yeah. But in principle, when the shell crossing happens, there will be probably some periodicity for the velocity. I wonder.
So in the shell cross region, it looks like this. So you do not want to compare this with your data, of course. But then there's ways you can fix this up, right? And also in the other models, it's wrong on those scales. So you have to do something.
Sure. Yeah. Thanks.
So when you said that you included baryons, what do you mean by baryons? Because I suspect you don't have any hydrodynamical physics in.
So in this stuff,
Yeah.
no. So here the problem was that, believe it or not, the accurate linear evolution of baryons in the absence of all pressure effects on very large scales, it was not possible to do this correctly until recently. And so what you got is really like, it's off. It was off. So there was a whole thing how you put this in. At first order, people knew, but then if you at first order just displace your particles slightly differently and absorb sort of the relative difference between baryons and so maybe one step back. So the problem is that baryons and dark matter do not trace each other perfectly at the starting redshifts of typical simulations, right? And so you see here, this is redshift 5. There's still sort of 5% off or something like this. If you go way higher, it's much, much more. And this is an effect is basically that baryons start only at recombination to fall. And so dark matter has a head start and it catches up. This is mostly neglected in all big simulations to this day. But so I think the next generation should probably put this in because. Yeah.
What's the problem with this? I don't get it. I've been doing it for years.
But you're using grid codes, right? You're using grid codes. So if you have two particle codes, for particle codes, this doesn't work. Of course. Yeah. It's for particles codes, or for if you do two just n-body simulations, right? When you completely neglect any pressure effects on small scales. Yeah. Yes, I should have said that. Sorry. Yes, that is a valid correction. So AMR codes have always done this correctly. Yeah. Now, apart from having it set up in the first place with the correct. Because you only typically they set up only linear perturbations. So SPT perturbations, not LPT perturbations.
So when you ask question, please speak loudly especially for online participants. Okay, Robbie? Oh, yeah, I'm sure you could.
Thank you. So this is about when you're in the multiple shell-crossed regime. So there are excursion set treatments that are trying to get around this problem. Mm-hmm. And I wonder if you've looked at the match between those treatments and...
We're working on that actually right now, so...
Okay, that'd be great.
So we should actually talk at some point.
Any other question? Joanne? I guess you just partially answered this, but I wondered what the next steps were besides what Ravi just asked about. What things you're going after next?
Well, so I think exactly sort of can we go further in the shell? Can we sort of tame the shell crossing regime? I think this would be fantastic. And so we know in some simple cases, or from the other way around, there's of course exactly what Ravi was saying from excursion sets. There's a very long tradition to exactly do this in the field, and yeah, so I think it would be great to sort of bring this together at some point.
So if you're doing Zoom simulations, like so quite small scales, my question is like, does it matter the NLPT corrections, and can you do it with? Because I know that at some point you couldn't do Zoom setups with the NLPT. Is it something solved? And should I?
So we have forever since the original music. Oh, okay. We have 2 LPT.
Yeah,
but even higher. I don't think it's relevant that much, but I don't know. I think for Zooms anyway, they are mostly used still to this day for more phenomenological studies. So I don't know how relevant it is. You might want to do it when you do like Zooms in the sense that you want to have a, I don't know, 100 gigaparsec box and have then a 1 gigaparsec Zoom in it or something like this. Maybe there you do care about such things.
Any other question? Dick?
Yeah, I just want to go after for a minute the idea of actually being able to do highly complex shell crossing, which is in effect, as you showed at the, I think it was you, at the very beginning, you did the 1D. And the description of what's actually going on is, you know.
This is the one where it's
this thing, yeah. As it wraps, what is in effect occurring is you're generating delta V squareds, that is to say entropy, that is to say heat. Surely that's fundamental to put in, rather than trying to do it to a d to the n order expansion, since, you know, that's sort of the physics of what's going on. It's effectively a, it's got features of a shock, in fact.
Yes, of course.
So what is the great advantage of trying to do a perturbation theory to such high order, given that it can't, I don't see how. I mean,
the original perturbation is simply this. You see this, right? So basically this tells you, if you want to have your power spectrum for this kind of resolution of simulation and all these caveats, if I want to have 1% accuracy, I can just use a higher order perturbation theory and then run my simulation for much shorter time. And it's cheaper to do this perturbation theory than run the simulation for a longer time. Right?
Yeah, but it's going to be dependent upon the specific region you're in, how much shell crossing you get, which means that...
No. I mean, this is really like, if you compare a Zeldovich initialized and a 2LPT, you see visually, you flip back and forth, you see the structure moves around.
Oh, no, I realize all of that. It's just that trying to push this thing so it's a high order perturbative scheme to try and do something.
In this case, it's trivial, right? Because you have the recursion relations, so you just turn that into an algorithm and you can do it numerically.
Yeah, but do you get the asymptotic expression of the...
Yeah, so this is what we're exactly working on. So for the 1D case, we did, right? And there you see that it is basically, this was the, where was it? This thing. You see that basically what's happening here is you have to absorb this singularity in your expansion, because it's a non-analytic function and you're doing a Taylor series effectively, so it cannot work. So it has a lot of similarities to standard phase transitions, and in fact you can determine the critical exponent for this thing here, what's happening from going from infall phase to virialized phase in the spherical case. Now, can you extend this to multi-D? That's where we're at. Yeah. I think it would be nice to do this, but it's the next step. And I fully agree with you. The conversion to internal energy degrees of freedom is exactly what's happening. But then there's people also thinking about this.
Yeah, but I don't want to keep going on. But you talked about renormalization methods to try and do the stopping, which is probably, I mean, I didn't really see that coming out of your methodology.
But this here is just the old Goldenfeld, whatnot, ODE renormalization. So you absorb secular terms into renormalization of the integration constants.
Okay, one quick questions, maybe for them. Okay, I have questions. So can this technique can be used to simulate this fuzzy dark matter? I mean, different kind of dark matter?
It's the same. It's just the same. It's the Schrödinger
would be
equation.
Very useful actually to deal with the fuzzy.
It's the same. It's the Schrödinger equation. The only key is that you're not solving exactly the same. You're solving a Schrödinger equation which maps onto Zeldovich or variants thereof. Versus in the other case, you're solving a physical Schrödinger equation. Yeah.
Okay, let's thank the Oliver again.